Everyone's got it. Okay, let me just do my announcements quickly. Are we still good?
I think you're good now, yeah.
Great, thank you. Announcements. Prom set 6 is due tomorrow. You guys know that. Okay. The other announcement is we finished phonons, which means we finished Macquarie chapter 11, right? So finished reading Macquarie chapter 11. And you know, there's some stuff in Macquarie chapter 11 is a little more extensive than we discussed in class. That's fine. It's fine to learn some extra material. Okay, and we're going to start a new topic today, and we're going to switch to this book. So I told you at the beginning of class, we were using this book for the first 2 weeks in the review of Thermo, kind of followed Chandler, and then we switched to Macquarie, and now we're switching back to Chandler because Macquarie doesn't have the Ising model. I don't really know why, to be honest. It seems like a glaring omission. And so we're going to stick with Chandler for pretty much the remainder of the semester. And we're going to stick with Chandler chapter 5 and 6. So chapter 5 is the Ising model. Chapter 6 is Monte Carlo. We're going to combine the two. Because I think it's best to talk about Monte Carlo in context of an application. And the perfect application is the Ising model. And in fact, that's why we're doing it. That's one of the main reasons why we're doing the Ising model. So we can introduce Monte Carlo. So start reading. So we're going to switch textbooks to Chandler. And so you guys should all have, there should be a PDF of this on Canvas, right? So just use a PDF. And so start reading chapter 5. You know, my warning is that Chandler, okay, he assumes a very, very high level. Right, so when you read Chandler, you can see that his explanations may be kind of terse, right? And he may jump to conclusions that he thinks is obvious and may not be so obvious. He may just present a result and say, derive this result. Right, so for example, we're going to talk about the one-dimensional Ising model, and Chandler's just going to give you the result and say, verify that this is correct. You can, where is it? Here you go. Page 122. He gives the result for the 1D Ising model and says, verify this result is correct for large n. As if it's trivial. He thinks it's trivial. I don't think it's trivial, right? So we're going to go over it in class. And so that's the catch with Chandler, is it's that kind of discussion. So just be aware of that, and I'll try to cover, the details. Okay, so does that sound good, everyone? Yeah? Okay, so is this part any better? Maybe I'll stick to this. So, new topic today. Let's get started. How am I over here, John? Is this good?
Yeah, that's fine. You have more room actually if you want.
Here?
That's good.
Okay, great. Oh, maybe I'll switch it back to another. So, the Ising model. Why are we going to do the Ising model? So that's our new topic. Ising model. I guess before I start, any questions about phonons? I hate to end a topic on a video. Any questions from the video? We can talk about phonons more in office hours. You'll have a couple of homework problems on that. Anyway, if questions come up, we can talk about that. But for now, I'm going to conclude it and move on. Okay, Ising model, in parentheses, we're going to put Monte Carlo methods, right? Because we're going to one of the purposes of doing the Ising model is to introduce you guys to computer simulations. And it's the simplest system we can do Monte Carlo. Okay. So when you first see the Ising model, especially as a chemist, you think it's like kind of abstract and irrelevant, but it's not. It's a model of spins, and so we're thinking about spins on a lattice, and so you have to use your imagination a bit to see how it connects to chemistry. But if you're able to use your imagination, you're able to make a lot of really powerful connections. And so if you ever think, oh, this is irrelevant to chemistry, you just need to use your imagination. Okay. So why are we doing the Ising model? Okay. Number one, it's the default model you use to discuss phase transitions, right? And so we're going to discuss phase transitions. And if you want to discuss phase transitions in statistical mechanics, you always start with the Ising model. Two, even though it's a model, you can form a lot of connections to real systems. So you can form connections with many different real systems. Say a variety of real systems. Right, so the Ising model is a model for a magnet, spins on a lattice. So you can obviously treat magnets with the Ising model. Okay. You can treat lattice. You can treat gas absorption, surface physics, really. Surface physics, say absorption. And if you use your imagination more and more, these possibilities are endless. I wrote down a couple papers in case I think it is really important for you guys to realize that the Ising model can be used in research. So I pulled some examples from the literature. You can even treat things like supercapacitors, which is something I study. So you can model supercapacitors, ionic liquids. And if you don't believe me, I just want to give you a couple of references. So here's a reference, kind of recent. The reference is Bosom et al. This is in JPhys Chem Letters, one of my favorite journals. Okay, JPhys Chem Letters, 2015. So pretty recent, right? You can still publish a paper using the Ising model, volume 6, pages 2644 to 2648. Okay? And this is a combined experimental theory paper. If you read the paper, actually most of it is experiment, but David Limmer, who's a professor at Berkeley, is on this paper, and he develops an Ising model to explain the experimental capacitance behavior that they measured at Princeton. And so, if you're interested, just look at this and you can see how, Ising models can be used in research. So, the reason I'm belaboring this is once we get into the details, it's important to keep in mind how it can connect to real systems. And the third motivation is to introduce computer simulations, right? Because if you go further in statistical mechanics research, you're inevitably going to use computer simulations. You're either going to use Monte Carlo or molecular dynamics. We're going to do Monte Carlo. Molecular dynamics is more popular, really, but Monte Carlo is very elegant and very powerful. Okay, so that's my motivation. Everyone happy with this motivation? Okay, so what we're going to do is, before I even tell you the Ising model, if you read Chandler is going to focus on number 1. Okay? So we're gonna, a big part of this discussion is gonna be on phase transitions. And probably many of you haven't spent a lot of time thinking about phase transitions. And so what I wanna do is give a little background on phase transitions, just to sort of set the stage for the types of things we're gonna think about. Okay, so let's start with a background on phase transitions before we jump into the Ising model. Okay, so background on phase transitions. Okay, this marker is dying. Did I not bring a better marker? Huh. Well, if it gets too bad, I may have to run up to my office and get a better marker. That one's dying too. Let's see how long it lasts. We might take I might give you a 2-3 minute intermission while I run up and get a better marker at halftime. Okay, so has anyone ever heard of people talking about phase transition as a first order phase transition, second order phase transition? So that's an important way to classify phase transitions. Okay, so of course what we mean by a phase transition is a change in state of matter, right? And so phase transition, of course, is a change in state of matter and there's obvious examples and there's less obvious examples. And so, of course your obvious examples are solid to liquid, whatever, liquid to gas, that's obvious. But there's more examples are not so obvious. Like anytime you have a system that's ordered that goes to disordered, that's a phase transition too, right? So you don't necessarily have change the state of matter or ordering or order of system. Okay, so we need to make it more comprehensive. So this is obviously changing the state of matter, but we could also go to, say, amorphous to crystalline. Okay, that's a phase transition. Glass to a crystal is a phase transition, right? If you have a bunch of surfactants, anyone ever work with, anyone ever heard about lyotropic liquid crystals? Lyotropic liquid crystals are, you put a bunch of surfactants in water and mix them in a jar and see what happens. and what will happen is if you mix surfactants with water so if you're at a low surfactant ratio, you have soap. Okay, that's not interesting, but it's a little interesting. You form micelles, right? But then if you change the ratio and you have a really high concentration of surfactants to water, like 70-30 or 80-20, you form what are called liquid crystals. And you can form a lot of different phases of liquid crystals. You can form lamellae, gyroid, hexagonal packed phase, and all of those are phase transitions between those states, right? So that's a change in ordering. So if another phase transition could be, say, a change in order of a liquid crystal, right? And you know this from basically electronics, right? You have a display that's transparent, and all of a sudden your display becomes opaque. How did that happen? Because you applied an electric field and you changed the ordering of a liquid crystal display, right? So you can change the ordering of an LCD by applying electricity, and that's a phase transition. Okay, so we have all these different phase transitions. We want to understand them. And so the first thing we have to do is classify it, right? And so the first important thing is classification. Okay. And here's where we talk about whether a phase transition is first order, second order, etc. So let me just write this down and we'll talk about it. So phase transitions are classified. I'm going to give a definition that's a little obscure, and then we'll have to talk about it more. Classified by the lowest order derivative of the free energy. Okay. By the lowest order derivative of the free energy that is discontinuous or divergent. Of the free energy underline free energy that is discontinuous or divergent at the phase transition. Okay? And so what we do is, if we know the free energy of the material, or we can do an experiment, we look at derivatives of free energy. So derivatives of free energy, we'll write this down, can be things like the energy, the enthalpy, the entropy, okay? And we say, okay, is a property that's a first derivative of the free energy discontinuous or divergent? If it is, we call that a first order phase transition. If we can't find any property that's a first derivative of free energy that's discontinuous or divergent, then we go to the second derivatives. And we look for discontinuity or divergence in the second derivatives. And if we find those, then it's the second order. So the best thing is just to give an example. Okay, so really, usually you just talk about first and second order. So first order phase transition is the first derivatives are going to be discontinuous or divergent. Okay, first derivatives are, say, discontinuous, etc. And for second order phase transition, it's their second derivatives. The first derivatives are continuous, okay? Second derivatives are discontinuous. So first derivatives are not discontinuous, are continuous. So we have to get the second derivatives. The second derivatives are discontinuous. Okay, so I'm writing so low. Derivatives are discontinuous. Okay? So even though we haven't discussed what these derivatives are, everyone agree that that's a well-defined definition? Look at the free energies, look at the derivatives. If the first derivatives are discontinuous, we call that a first order. Okay, so let's give an example. So let's look at these phase transitions, and your most common phase transitions are first order phase transitions. Okay, so if someone asks you what order is a phase transition, if you guess first order, that's probably a good guess. Most common, okay, first order. Okay, and these are most common. And so these are basically phase transitions where you change the state of matter, right? So this is solid liquid. Liquid, gas, solid, gas. Okay. So I'm telling you these are first order, and so it means something's going to be discontinuous. The easiest thing you can think about is the density is discontinuous, right? I mean, obviously, if we're going from solid to liquid, the density is changing. If we're going from liquid to gas, and so the density is discontinuous, and that gives you a clue that it's first order. Okay, so that's rule of thumb. Think about that. Does the density change in my phase transition? If it does, you're always going to have a first order phase transition. Okay, so the extensive variables are discontinuous here. The the energy, the entropy, enthalpy, density. Okay, I'm using rho for density. Okay. These are discontinuous across the phase transition. Okay. And right, the density is obviously discontinuous. Energy and enthalpy are too, right? Because you need to put in energy to evaporate water, right? So the energy of the liquid obviously has a different energy than the gas. The entropy of a gas is obviously different than the entropy of a liquid, right? Does everyone agree with this? These are also first derivatives of the free energy. Do we know that already? Do we have we seen a formula before for the energy that looks like a first derivative of the Helmholtz free energy?
The AT.
Yeah.
GB.
Exactly. D beta AD beta, right? Right? These are also first derivatives of the free energy. Right? And so you can look in Macquarie table 3.1 and you can see the formulas for how we get these from the canonical partition function. Of course, we're going to relate log Q to A, and that's how we get the first derivatives of the free energy, A. Really, any free energy, but let's just write A to be specific, right? And so an example is E is d beta A d beta, right? And so again, it's a first derivative of something that looks like the free energy, and you can write other derivative expressions for those. Okay, so does that make more sense? What this definition means? Note that, so the extensive variables are discontinuous across the phase transition. What about the intensive variables? Mu, P, and T. Those are continuous because those are my condition for equilibrium, right? So note that intensive variables are actually continuous. Across the phase transition, right? And this is basically mu, the chemical potential, the pressure, and the temperature, right? Those, my conditions for equilibrium between my liquid and gas depend on these being equal for the two phases. So those aren't changing as I go from liquid to gas, right? Our conditions for equilibrium are same in both phases at equilibrium. Is a phase transition an equilibrium process? It's a tough question. It is, because it's reversible, right? And so any process that's reversible, you say, occurs at equilibrium, right? Because you can shift it one way or the other by just tweaking conditions slightly, right? So if you have water and you're at 100 C, you're going to boil it. You're going to convert it from, liquid to gas. But if you drop the temperature to 99 C, it's going to condense in the liquid, right? So just by doing a slight adjustment, you can go one way or the other. And so phase transition is an equilibrium process. And so these have to be the same as you're changing that phase. Well, it can be. You can have a phase transition that's non-equilibrium, but usually we talk about phase transitions that happen at equilibrium. Okay, so this is, unfortunately it gets more complicated from here. The first order are the easiest to understand. The second order are a little tricky, Unfortunately, the Ising model, as we'll see, deals with second order phase transitions. And in fact, the statistical mechanical theories for first order phase transitions are still an open research question, right? So it's very, very difficult to develop a theory from first principles for first order. So the reason we do second order is because, well, it applies to some materials and it's what the Ising model gives us. So if we go to second order, phase transitions, okay, we don't have as many examples here. They're not as common. And so if we're going to have a second order transition, it means these things must be continuous. Okay, so the first order derivatives are continuous. So E, S, H, and rho are continuous across the phase transition. That's why it's not first order phase transition. But there exists some second order derivatives which are discontinuous or divergent. Okay. So second order derivatives and so what's an example of a second order derivative? The heat capacity. Why is the heat capacity a second order derivative? Well, the energy is a first order derivative of the temperature, essentially, and the heat capacity is a derivative of the energy. Right? So the heat capacity is second order derivative. You can write it like this. You could write CV is a temperature derivative. If you plug in log Q for this, and you convert this from a beta derivative to a temperature derivative, you get a factor of kBT squared in front, d log Q dt. Right, so that's a expression for the heat capacity, and obviously we have two derivatives of temperature, and log Q relates to A. Right, so heat capacity is second, so this could diverge, might be discontinuous or diverge. So you could look at the heat capacity. Okay. That's fine. We're going to deal with essentially ferromagnets, right? Because the Ising model is a model for magnetic phenomenon. And in that case, you talk about something called a magnetic susceptibility. And I'll just define it now, and we'll discuss it. We'll discuss it more later. So for ferromagnets, which is the case, what's the most common ferromagnet? Iron, right? So what is a ferromagnet? A ferromagnet is anything that holds a magnetization in absence of an external magnetic field, right? So that's a ferromagnet. We'll talk about it more. So e.g. iron. The second derivative we usually consider is what's called the magnetic susceptibility. We'll talk about this more. It's essentially how the magnetization changes when you apply a magnetic field. Is defined by chi. So chi is the parameter for susceptibility, and is defined as 1 over n d squared log q. That's my free energy. I have a second derivative with respect to d beta h squared. Okay, where h is an external magnetic field. Okay, so h is external magnetic field. And so here we have to take a second derivative of free energy with respect to an external magnetic field. We'll talk about that later, but for now, the point is that we have a second derivative of free energy with something, and this is going to diverge. Okay, so for a first order phase transition, suppose we're back here. Is the heat capacity continuous or does it diverge in the phase transition? Trick question, kind of. It diverges, right? If the energy diverges, then the derivative energy diverges. So that's the trick. It's not that this doesn't diverge for a first order phase transition, it's that there's a lower order derivative that diverges. Right? So little tricky, it's you define it as the lowest order derivative. So these things always diverge for first order. It's just you go to the lower derivatives. So little subtle point. Okay, so that's just some definitions. That's classification. So any questions, classification? So one more thing before we introduce the Ising model is I want to draw a phase diagram and I want to define critical points. Okay, so a fundamental property of we're gonna be detectives. We're gonna solve the Ising model and we're gonna search for a phase transition because we want to find the simplest physics that lead to a phase transition. And the first thing we're gonna try isn't gonna work, right? So we're gonna have to keep hunting that until we find it. And so we're looking for key things to signify we have a phase transition. These are one thing we're looking for. Another thing we're looking for is a critical point. Okay, so a fundamental property of phase transitions is the critical point. Let's just say phase equilibria. Is the critical point. Who has a good sense of what a critical point is? We kind of talked about this a little in 3411, right? Just a little bit. Okay. The thing I like most about doing this computer simulation of the Ising model is you're going to get a movie of what the critical point is. Okay, and a picture's worth 1,000 words. So when you watch a movie of the Ising model, when you simulate it near the critical point, you're going to understand qualitatively what a critical point is better than anything I can write on the board. Okay? So if you've ever been, wanted to know more about critical behavior, you're going to see it with your own eyes when you do these simulations. So that's something I really like about these simulations. So let me just define it and we'll talk about it. So to talk about a critical point, you need to draw a phase diagram. I hope you drew a lot of phase diagrams in undergrad thermo. And for some of you, if you didn't, then that's my fault, right? But we did. And so we're going to draw a phase diagram. What is a phase diagram? Well, what you do is you draw different phases of matter on a coordinate system, and your coordinate system, you choose two different thermodynamic variables. One is almost always the temperature. The other could be a variety of things. It could be the pressure, it could be the density. For the Ising model, it could be the magnetization. Here we're going to choose temperature and density. Okay? So we're going to put temperature on the y-axis and density rho on the x-axis. Okay, so this is density. Okay, and it's good to be able to sketch out a common phase diagram, liquid gas phase diagram on a temperature density curve. Okay, so think about water. So if we were going to put water on this phase diagram, we'd have the liquid at high density, right? we'd have the vapor at low density, and what would we have in between? A coexistence region, right? So what you do is you draw a curve, which looks like this, kind of. It's asymmetric because it's steeper on the gas side, and it's slower decaying on the liquid side. And over here on the high density side, you have the liquid, so you write L. Over here you have the gas to the left, and you hit a peak, and the apex of this peak is your critical point, right? And so this is your critical point here, right? And because you're on a graph of density versus temperature, your critical point is characterized by a value of the density of the critical point, you would call that the critical density, and a value of the temperature of the critical point, you would call that the critical temperature. And so you could characterize this by Tc rho c, would be the values of the temperature and the density of the critical point. Okay? So let's just get on the same page of phase diagrams before I talk about the critical point one. It's really important to have a picture in your head of what happens to a physical system as you move on this diagram. So, what happens if I'm in here? First of all, can you prepare a system? Suppose you have water, right? Can you prepare a system at any given density of water? That's a little tricky. You can't prepare the liquid at any given density, but you could prepare the total system at a given density. You literally take a fixed volume, take a beaker, 1 liter, and you just pour some amount of water into that beaker until you have the right density. You agree with me?
Are you saying that the density is like taking into account the air and the rest of the empty space?
Take it there. Have a beaker. Have it vacuum.
Yeah.
Right. Pull out everything out of the beaker. Experimentally, it may be hard, but you could suck all the air out of a beaker. You don't want to make it out of glass because it would break, but make it out of something else, right? And suppose you have a 1 liter jar with vacuum, and then you could put 1 mole of water in. I could put 1.5 moles of water, and I could put 2 moles of water in. You could do that, right? No? People are confused. Couldn't you do that?
There's some like
Why not?
cohesive stuff holding water
change the
together.
density of the water.
Yeah.
But that's the point. You're not thinking about the density of the water. You're thinking about the density of your whole system.
Okay.
If I'm defining, if my beaker is literally 1 liter. That's my volume. If the water doesn't want to explore the whole liter, that's the water's problem. Right? I'm giving the water a liter of volume. Right? That's how much volume it has. I put 1 mole in there. The density of my system is 1 mole per liter. Right? Yeah, if I put 0.1 moles in, the density of my system is 0.1 moles per liter. And if the water wants to, form droplets or something, that's up to water. But I'm still defining the density as 0.1 moles per liter.
So is that why you're saying that density is extensive? Because you're defining it as a
The density is intensive.
But we just wrote extensive variables fit density.
Oh,
That's why
I'm
super
sorry.
confused.
Right, I'm sorry. Sorry, this should not be in the extensive variables. Sorry, I got a little sloppy. These are extensive variables, and density is intensive. So, plus rho. Okay, mostly the extensive variables, and this, so the density in the canonical ensemble, NVT, is fixed in the canonical ensemble. So really, these are the formal quantities you're looking for. The reason I put density there is density is kind of your hint. If the density is discontinuous, it hints that these are also going to be discontinuous. Anyway, good catch. So everyone agree with me, right? That in principle, I can prepare a system of water at 0.1 moles per liter. Yeah. Okay. So suppose that's right here. Suppose this is 0.1 moles per liter. I prepared my system at this density. I've just thrown in 0.1 moles. And then you're right, John. Then what? Then water has to decide what it's going to do. Is water going to make a, dilute, just phase at 0.1? No, it's not, because that's not stable. So what's water going to do here? It's going to move up, right? You're going to pick a temperature, so you're going to prepare your system at this density, this temperature. So that's how I prepare my system. And then what it's going to do, it's going to move out to the line, right? So water's going to move this way to this line, and it's going to move this way to this line. And so you're going to get a phase coexistence where you're going to get water vapor at that density, and you're going to get liquid water at that density, right? So that's what the phase diagram tells you. It tells you if you're a crazy experimentalist and you shove 0.1 moles of water into a 1 liter vacuum container, this is what you get at equilibrium. You get a phase, because water can't be at this density, so it has to phase separate, right? And it has to go over here and it goes here. And so the curve tells you the density of the liquid at equilibrium for a given temperature when you're on a phase coexistence. And this tells you the density of the gas at equilibrium at this temperature when you're at coexistence, right? And how much you have is you just have X, some amount, times the liquid, times rho of liquid, plus 1 minus X times rho of gas, must equal basically the density that you prepared. Right? That's how you figure out the composition. It's just, this is your density of the liquid, this is the density of the gas, and you have a fraction of the liquid and a fraction of the gas, such that when you sum the linear combination, you get 0.1 moles per liter. So the phase diagram tells you everything about what your system's going to do when it equilibrates. It tells you the density of the phases at coexistence, and you know how much you have by just solving this little algebra, right? Because obviously the density has to be right. The density has to be, the total density has to be this. Okay, so I hope I didn't belabor the point, but that's an important thing to get in your head. So everyone okay with that? That's what we use a phase diagram for. Is figuring out coexistence. Okay, so and so what is the critical point? The critical point's where we don't have this concept of phase equilibrium anymore, right? We've hit some magical temperature where the system can no longer separate into a liquid or gas. And so that's what the critical point is, right? So the critical point, so the critical point has, and above, okay, the critical point and above, right? Temperatures above the critical temperature has no concept of individual liquid or gas, right? Of distinct liquid or gas. So how can we have no concept of distinct liquid or gas? To have a liquid or gas, it's got to be a stable phase, right? If you think about our second week of class, we talked about conditions for equilibrium and stability, right? And in our second week of class, what we did is we drew a diagram where we drew a diagram of the free energy as a function of some variable, right? And we said for a system to be stable, it's got to be a minimum of that free energy function. Right, so I think you'll trust me that a stable and a liquid gas look like this. Okay, stable liquid and gas looks like, okay, if we drew the free energy, suppose I'm making a plot, okay, and what should we use? Gibbs free energy, Helmholtz, I don't care. Let's use Gibbs. Might as well use Gibbs. So I'm gonna plot Gibbs, G, okay. I need to plot a parameter on the x-axis that lets me distinguish between the liquid and gas. What's a good parameter for that? The density, right? Because the density easily distinguishes liquid gas. And so here I'm going to plot density rho. And so qualitatively, right, how would I draw a system on this graph, say water, qualitatively, that indicates that water has a stable liquid and a stable gas?
You graph like 2 minimum.
Yeah, that's what I would do. So let's use colors. I did bring colors. So pretend we're at low temperature, right? Pretend we're lower than 100 C. I'm going to draw 2 minimum. Which one should be lower?
The water.
The liquid.
The liquid.
Yeah, right. So if I'm at low temperature, okay, suppose we have a density of liquid, density of gas. So density of liquid is higher, right? So suppose this is my liquid density, rho liquid. Suppose this is my vapor density. Let's just use G for gas to be consistent. So that's the equilibrium density of my gas. And I'm gonna, to simplify my diagram, I'm gonna pretend my liquid density and gas density don't change with temperature. They'll change a little bit, but let's just simplify my diagram. And so if I'm at low temperature, a free energy profile should look like this. I should get a minimum here, hot like that, something like that, right? So this would be at low temperature. Okay. And so these phases are stable because they're local minima in my free energy profile. And the barrier is keeping them from easily interconverting, right? And my liquid is my thermodynamic, is my phase at equilibrium because this barrier is lower than this. I would get a positive delta G if I went from here to here, so it's not going to happen. So at higher temperature, they're going to switch, right? So at higher temperature, maybe the total free energy is going to go up, but maybe it's going to look like that. Okay, so this is maybe a higher T. Right? And maybe there is a barrier here. Maybe it's a smaller barrier. Right? And so now my gas is equilibrium phase. The whole reason I'm drawing this diagram is now maybe, just maybe, you can envision what this looks like at the critical point. Flat. Yeah. Near the critical point, it's going to look like that. Okay? And so this would be at critical point. Okay? So that's what critical behavior is. You hit critical behavior when you no longer have your minimum wash out of your free energy profile. In principle, you could compute this with a computer simulation or something. From an experiment, you can get the curvature. The barrier washes out, and so therefore the minimum wash out. And if you don't have any minimum, then you don't have a liquid or gas. And so what's my system gonna do, right? So if I'm here, what my system's gonna do is just gonna rattle around this minimum, right? Think of a ball rolling on a hill. I'm gonna be around the density. My fluctuations are gonna be low. I'm always gonna be looking like a liquid, right? If I'm up here, I'm gonna rattle around here, right? In the gas minimum. So I'm always gonna be looking like a gas. If I'm in here, what am I gonna do? I'm gonna go all over the place, right? So if I'm here, oh, wrong marker. I'm going to explore the whole thing. I'm going to go all over the place, right? And so that means the critical point is characterized by huge fluctuations in density, right? Because I'm no longer constrained to a minimum. I'm exploring the entire range of density. So critical point, let me switch back to my black marker. Right, so, oh, wrong one. My marker's running. Maybe we should, okay. Critical point is characterized by huge, even diverging fluctuations. Right? Everyone agree this is a fluctuation? If I'm exploring the density, my density is just fluctuating from low to high, just back and forth. Say in density and other properties. Okay. Primarily we think about fluctuations in density. So I think these two qualitative pictures are really important to understand. Phase behavior, this is what you think about happens at the critical point. Qualitatively you can imagine that this gives huge fluctuations, and you'll see a movie of this in your Ising model. Okay, so you will see a movie of this. A movie of this in your Monte Carlo simulations. And so when you do Monte Carlo simulations, you're going to create a movie of your spin system, and when you hit the critical point, you're going to see fluctuations. Okay? And so I think you'll really understand qualitatively what critical phenomena is. Okay, that's my background discussion on phase transitions. Any questions? Was that helpful to go over that? Was that kind of new? Okay, so I'm glad I went over that. So this is the kind of stuff we're thinking about, right? We're trying to explore this physics, and our goal is to come up with the simplest model, because we like things to be simple. The simplest possible model that can describe these effects. So we're going to introduce the Ising model. We're going to start with the simplest case. We're going to realize it's not good enough, and we're going to have to make it slightly more complicated. Okay, so can I erase this? Actually, no. Let me leave this for a second. Let me come over here. Okay, so the Ising model. Okay, and the Ising model is the simplest possible model that can reproduce phase behavior. Okay, so that's why it's widely used in physics. Simplest possible model we can come up with that reproduces phase transitions. Right? So if we want to study a phase transition, we need a model that can reproduce a phase transition. That's the Ising model. Okay, so here's our plan when we do the Ising model. Let me just write down the plan, just so you know we have some organization. My marker is really fading fast. I'm going to give you guys a 2-minute break. I'm going to run upstairs. Usually you're supposed to give breaks when you teach a 75-minute class. We just have so much material to cover. 2-minute break. I'll be right back with another marker.
Whoa. Free time. When do we ever get this?
Now time to explore all over again.
Whoa, I'm getting the,
You
standing
stand
up
up a
too
little too
fast.
fast.
Crazy.
Oh,
Going
God,
wild in
I
here.
agree.
Oh, we're recorded though. So we can't go that crazy. Should pause the recording.
2 minutes of silence. 2 minutes of us chattering in the background. Actually, has anyone listened to the recordings? Can you hear when people ask questions? Or like...
Yeah, you can
Oh,
hear
okay.
people ask questions. I don't know. I mean, the one recording I really watched all the way through was like the one that we had the other day. Yeah, I haven't watched
one person that's online.
Yeah, there's one
included.
person that's really online.
Yeah.
Wow.
So
That's
that would
crazy.
that would be a bummer. You know,
Mhm.
to be that person.
But I actually see board because I think the first videos people even.
Oh, no.
Well, a lot of the first videos you can't even access. Like I've tried
What?
going back and accessing. Maybe it's
I
just
don't know.
me.
I don't
But
know.
like-
Like I know that my computer, like sometimes the formatting, you can choose different formatting on Canvas to
Yeah.
the videos, and some of them don't work on certain.
Was that 2 minutes?
Search like search like
You know, when I teach in Mosey,
just open them in YouTube.
I'm too casual, right? Because my office is right there. And so before class, it's like, well, I could check my markers, but my office is right there. So when I teach in a different building, Rebecca and Pablo and Kevin know, I'm really careful to have good markers, right? That's a
Then
lot.
leave them untapped.
But then you post them, yeah.
Well, sometimes you get distracted, right? So, these are brand new, so if they're not good, they're not my fault. 'Cause they're brand new.
Yeah, since you have like 3 markers in your hand at a time, you
Yeah.
have
Yeah.
those, right?
All untapped.
You know, when you're thinking about statistical mechanics, your
Oh,
mind is
he'll-
just.
get
he'll
carried
tell
away.
you
You're
how annoying I used to
distracted.
get with them. I used to sit up in the front of the class and
And just-
yeah, and no, like at the end of class, I would seriously go up and tap his markers.
Is that
Again,
really?
Every time.
So you saved me for the whole semester. Wow, I owe you. I owe you a coffee or something. Maybe
Wow.
next spring I should tell whoever's gonna TA and just say, please pay attention to my markers.
Have my markers.
Well, yeah, you would just like pick up 3 markers at once because you wanted to do a colored picture,
Yeah.
and then you would set them down uncapped and just leave
Wow,
them.
just absent-minded, right? Just really absent-minded. Okay. Anyway, markers. That's why you need a surplus of markers, right? Because you can't count them. You need like 20 of them. Okay, so our plan is this. Let me tell you the plan, because it's gonna seem like we're jumping, but we do have a plan. The first thing we're gonna do is we're gonna try to solve the 1D Ising model. Okay, so we're gonna solve 1D, and we can do this. Exactly, analytically. Okay. And if 1D gave us a phase transition, we would be done. But I'm gonna give away the answer. And so 1D is not gonna give us a phase transition. And we'll explain why. Okay, and that's a big problem. So we start simple and we say, oh, it doesn't work. We learn something because we can sort of hypothesize why it doesn't work. So we need to go to more complicated. So we need to go to 2D, right? And so when we go to 2D, we are in trouble, okay? Because as you'll read in Chandler's book, there is an exact solution of the 2D Ising model, but it's one of the greatest, Chandler calls it one of the greatest achievements of the 20th century. And he doesn't even qualify that statement as being related to statistical mechanics. He just says, period, it's one of the greatest achievements of the 20th century. I mean, with an unqualified statement. Okay. So we're not going to do it. So exact 2D Ising model was done by Onsanger. Okay, and it's really, really hard, And so this was, you don't have to take my word, you can take Chandler's word. It was a great achievement. Let's just call it a great achievement. And so what we're going to do is we're going to pull Onsanger's results from either Chandler's book or his paper, and we're just going to look at the results. So we're going to just look at results. Okay? And then what we're gonna say is, well, we don't want to work as hard as Ensonger, and so we're gonna do computer simulations. And so we're gonna say, well, we don't really need a closed form analytic result. We can get a numerically accurate result, and so we're gonna do it numerically. And so what we're gonna do is, okay, 2D Ensong grid achievement, look at results, and what we see in the results, it predicts a phase transition. Okay, so that's great. So basically what this tells us is the 2D Ising model is the simplest model we can use to study phase behavior. Not the 1D, we need to go to 2D. Why does the dimensionality matter? We'll think about that. Think about why the dimensionality might matter as we write down the Ising model. The world would be very, very different in different dimensions, right? In 2 dimensions, electrostatic forces would go as 1 over r, right? The Coulomb potential would go as log r in 2 dimensions. Things would be very different, right? So dimensionality governs the range of interactions, and so that's why it determines the physics. Okay, and so what we're going to do after we look at Ensong, we're going to say, okay, it's worthwhile to study a 2D Ising model. We're going to solve this numerically. So we're going to solve numerically 2D Ising numerically with Monte Carlo. Right, and we're all going to get out our Jupyter notebooks, right, and we're going to write a nice Monte Carlo code in Python using Jupyter. It's going to be fun. Okay, and that's going to be the final project. So that's the plan. So we only have 10 minutes left. All this talk about Ising model, let me tell you what it is. Okay, so what is the Ising model? Ising model is a lattice of spins. Okay, so in the Ising model, okay, we consider spins on a lattice. And let me put spins in quotes because the spins could either be actually what we mean, we actually have spins on a lattice, or the spins could be, like I said, use your imagination. The spins could be an analogy for something else, right? And all of this, when I say form connections to a variety of real systems, all you do is you map the spins to something else. So upspin could be a cation, a downspin could be an anion. Then you have an ionic liquid, right? An upspin could be a gas absorbed on a lattice. A downspin could be an empty lattice site. Then you have a surface lattice gas model, okay? And so we are going to think of the spins as being physical spins, but if you just use your imagination and you can map the spins to different things, then you have different physical applications. Okay, spins on a lattice. Let me note spins could be real. Or analogs of something else. Right, and it gave you examples, just write down e.g., they could represent a lattice gas. Right? And so in Chandler chapter 5, he discusses the lattice gas. Okay, so anyway, we're gonna have a lattice, we're gonna have spins. So draw, and really we're gonna be working in 2D most of the time. So think about it in 2D, we'll see how we can write a lattice in 1D, right? But most of the time we're gonna be in 2D. So just draw a lattice. In principle it's infinite, right? So we have infinite, 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 infinite. Well, when we write the Monte Carlo computer code, we're gonna have to talk about how we treat an infinite system. We always use periodic boundary conditions. Right, we'll talk about that and divide it up into a lattice. Okay, that's a bigger lattice than I wanted, but oh well. Right, and put a bunch of spins on it. Right, so this is bigger than I wanted, but the spins could be down, they could be up. I'll just fill in 2 rows and I'll stop. Okay, etc. Okay, so these are spins. These are my spins. Let's say we have n spins on my lattice. Sometimes it may be easier to say we have n by n spins if n is the number of lattice sites. So this just for now, say we have n spins. We can label, now I need to label each spin. Okay, so if I have a 2D lattice, the natural thing to do would be to label it by what row it's in and what columns it's in, right? I would need 2 indices there. The notation gets messy if I have 2 indices, because I'm gonna have interactions between spins, so then I have to write a spin with another spin, so to have 4 indices. And so what I'm gonna do now is just use 1 index to define a spin. When you write a computer code, you're gonna use 2. So for now, I'm gonna use 1 index I for a spin. So I'm gonna call this spin I. Right? And so what you have to do then is take your 2D lattice and just number them 1, 2, 3, 4, 5, 6, 7. Then you go to the next row, 8, 9, 10, 11, 12, 13. Go to the next row so that you just have 1 index. Okay, it just simplifies notation for now. Spin I, and the spin has a magnetic moment mu because the magnetic moment tells us how it interacts with something else. With magnetic moment mu. So we use mu for the magnetic moment of the spin. Okay? And so just note, let me just note here, I'm using 1 index to label each spin for convenience. For notation, convenience, but if you wanted to code this thing on a computer, the natural thing would be to use 2 indices, 1 for the row and column. Okay, but when you code this in, you will use 2 indices for each spin. I mean, you don't have to, but it's much simpler, right? It's much easier to keep track of, right? And your 2 indices will correspond to the row and column. Okay. Okay. So basically, we're going to write down equations for the Ising model using 1 index for the spin, and then just realize that you're going to use 2 indices later on. And what we're going to do is the spin can either be up or down, right? So each spin can be up or down. Okay, and so if I labels the index of the spin is going to be called SI, and it's going to have a value plus or minus 1, right? For up or down, right? So all these spins SI for the different lattice sites I can have a value up or plus or minus 1. Okay, and so each spin has a magnetization. Okay, so this is essentially the direction of the spin, whether it's up or down, times the magnetic moment gives you the magnetization. With magnetization, we call it M. Mi is the magnetization of the I spin, is just the magnetic moment mu times Si. Okay? That's the magnetization, and those are the values of the spin. Okay, so far pretty simple. Another thing we're going to do is we want to be able to sometimes, not all the time, sometimes we want to be able to bias the system. So we want to put in a bias and say, okay, I want to bias the spins being up. I want to bias the spins being down. We do that by applying an external magnetic field. And so what we can do is we can also apply an external magnetic field to the system. Just going to draw an arrow, okay? And we're going to use H for magnetic field. So we have to keep, we're going to have different H's floating around. Usually H is Hamiltonian, but here H is field. And so I'm going to use H to denote an external magnetic field. And we may have this, we may not have it. Actually, most of the time we're not going to have it, but let me just put it there because in general we could apply an external magnetic field. And so this is our construction, okay? And from here on out, we have to make choices on how complicated we want this to be based on how the spins are going to interact. Okay, and so this is the general construction of the Ising model. Okay. Now we have to make choices. Now we have to make choices about how the spins interact. Okay? And the choices we make are going to give us different Ising models, and some may be more realistic than others. And so when people use Ising models in research, basically what they're doing is they're making different choices on how they're going to let these spins interact. Then they solve the model and they say, oh, does that represent the problem that I'm trying to solve? And if the answer is yes, then they've learned something about the interactions. If their answer is no, they have to go back to the drawing board, right? And so our first choice is for the spins not to interact. That's the simplest choice. Okay, so choice 1 is a non-interacting Ising model. Okay, so choice 1. And we're not going to really spend any time on this. Non-interacting. Okay, so this is the simplest thing you can say. You have all these spins on the lattice. They interact with the external magnetic field, but they don't interact with each other. And so what we're going to say here is we're going to say the energy of my system. I'm not going to use H for Hamiltonian because it's going to get too confusing with H for field. So I'm just going to write E for energy. I'm going to put a nu on it because it depends on the state of the system, and right, so this is consistent with the notation I've used so far for partition functions. Nu represents a state of the system. And what it is, since my system is non-interacting, the only contribution to the energy is the spins interacting with the magnetic field, right? And so I have to sum over all my spins. My spins are indexed by I. So I sum over I equals 1 to n spins. The magnetization of the spin, Mi, interacts with the strength of the field. So if H times Mi, or substitute Mi for mu Si, right? And by convention, you put a minus sign there. So if the spin is aligned with the field, it's a negative energy. Okay, so this is just each spin interacting with the external field, right? So this would be the simplest energy function. Okay, and the state of the system, nu, well, how do I specify the state of my system nu? I have to specify whether each and every spin is up or down, right? So I have to specify all values of Si for all the different i's. State of system nu corresponds to the set, right? We use brackets for set, the set of all these Si values, right? Because specifying all the SI, specify whether all my spins are up or down. And so nu is just shorthand for this, and this is the energy, okay? And so you're gonna solve, you actually already know how to do this problem because this is a system of non-interacting particles, and we've done that before. And so you're gonna do this on your homework, okay? You're gonna solve this on your homework. Okay, so that you can do already, and you can do that. So I'm out of time. So this is the simplest case. You'll do that on your homework, and we'll have to go to the more complicated case next time. And that's what we'll do in class, when they do interact.
So why is it a set of SI instead of just like a vector of SIs? Because
Oh, you could think of a vector. It's
the
the
SIs
same
are
thing.
they're all going to be 1 or -1. So your set can only have 2 values in it, right?
No, it's
Well,
the
well,
set.
yeah.
The
Each-
set
each
There
one.
is
is
n values.
Okay, cool. I'm like
the set
who's
is the
set?
vector. So the set is just all possible. So it'd be S1. The set would be you'd have to specify S1, S2, S3,
Yeah.
Sn. So yeah, it would be the set is a vector.
Yeah.
It's a collection of all the values.
Okay.
Yeah, good point. Okay, so that is the Ising model, and you'll solve the non-interacting one on your homework. I used to make that an exam question, and then people got I used to make it a midterm exam question actually, before we ever talked about spins, and to see if anyone could recognize that it's really the same problem as you've done before. But then people were too thrown off by introducing spins and magnetization, so I decided not to make it a midterm exam question. Anyway, you'll do it on your homework.
What does the temperature versus density phase diagram include the solid phase?
Oh, if you have the solid, you would have to basically, the solid would be further towards the right.
What about with water though? Isn't
So
less
you
than-
don't have a critical point for a solid liquid. You only have a critical point for solid gas. And the reason is because of symmetry. You can only have a critical point when you have phases of the same symmetry. And it's called, I think that's called Landau's rule. And so the solid isn't as interesting because you don't have a critical point. You just sort of have a line.
Oh,
Yeah. Usually you don't draw the solid liquid on rho t, you would draw them all on pt. So usually when you include solid, you go to pressure, temperature.
yeah.
Because rho t, you're really looking at the coexistence and the critical. The solid's not interesting because it's not changing density that much. So, I mean, really what you have, right, is the solid and liquid don't give you much flexibility because you don't have a low density and a high density phase. So essentially what would happen with the solid is you would never have a solid. If you prepared a system at low density, you'd always have a gas-liquid phase coexistence. Because you could think, basically, a pressure is going to build up in that vessel. Right, so basically, suppose you take a volume with vacuum. Then you put 0.1 moles of water.
Somehow the water's going to turn into.
Some of it's going to evaporate, and some of it's going to stay liquid. And the part that evaporates gives you a pressure.
What if your temperature is
super low.
Very
like
low,
really
yeah.
low? So you
Yeah,
can
so,
use sublime.
right, so, okay, so the temperature is really low, then basically you would freeze it, and you'd have a solid gas coexistence. And,
But you can have a critical point between
No.
solid, liquid, and gas, right? For like CO2 stuff, right?
yeah, it's a triple point.
Triple point, yeah.
You can't have a critical point with a solid,
Okay.
with a crystal, because the symmetry prohibits it, because the critical point says that the liquid and the gas merge into the same phase, and that's not possible if they have different symmetries. So you don't have a critical point with the solid. So you're right, you could draw one for the solid and the gas at low temperatures. It would be pretty boring, right? Because it would just, the solid would stay the same density, essentially.
So would it be like if you drew a line like this going through that coexistence bit?
Yeah, basically you'd have, so basically you'd extend this diagram, right? So your solid would be down here. So basically, this isn't 0 Kelvin, right? I don't know where I meant here, but basically you'd extend this down. And so your gas would stay here, but then at some point when you change the temperature, you'd get a liquid solid phase transition. And so this line would turn into a solid line, a line for the solid.
But it would be a straight line?
It wouldn't be perfectly straight, but it would be,
Like close to?
it would be much straighter than this, because the density of the solid is not gonna
It's
change.
just shoots out.
Yeah, yeah. That's a good question. I haven't thought about that much. Usually you don't draw the solid on this kind of phase diagram as often. You do if you think about allotropes of, not allotropes, basically different crystalline phases of, say, carbon or something. Then you'd have a solid phase diagram. Where you'd have, in material science, you do phase diagrams a lot more than in chemistry. And they become really complicated. Because then you have a phase diagram for all your different crystal phases of a material.
Deal with that corrosion.
But still, you're usually in a pressure temperature rather than a density. So you usually don't think about solids on a density temperature. Usually you would do a pressure temperature.
We also did potential and temperature diagram.
Potential, like electrostatic potential?
Yeah.
Or chemical potential?
Electric.
I guess it's the same. Oh, that's interesting. For electrochemistry.
Yeah.
Yeah. What class was that?
That was corrosion.
On corrosion. That's
So
interesting.
you would put like attach an anode or a cathode to the metal.
Yep.
And then give it some sort of voltage and push it into a different crystal state.
Yep.
Which is more stable
Oh.
under given conditions.
Yeah. Huh, that's interesting. Yeah.
See, for something like that, if you like remove your voltage, would it shift back to the previous state, or would it stay now in that state?
Yeah.
Uh,
Like, if you're on a